So next in line is Thomas Breuer. So he's going to talk about the centralized dashboard for continuous benchmarking from HPC clusters to quantum processors. Thank you so much.
Good morning. Thank you for the introduction. It's nice to be back at HPC KP in hot and beautiful Barcelona. When I started benchmarking HPC clusters or applications several years ago, I collected the data in my own space, used custom Python scripts to visualize them, and they were hard to maintain. So I assume we are all either operating HPC systems or using them, or quantum processors, so you might relate to that. The centralized dashboard that I'm going to present you today would have made my work easier, and hopefully, potentially in the future, also yours. So my name is Thomas Breuer, and I'm working for the Jülich Supercomputing Center. Let's see what I need. Let me introduce first the infrastructure that we are going to work in. So we have a bunch of supercomputers from different kind of hardware vendors. Many companies are involved, different software stacks. We have also many computing storage clusters there, and currently our biggest one, you might have heard about it, is Jupyter, the exascale system, the first one of Europe. And we already have these quite heterogeneous cluster environments, but to make this a bit more complicated, we have also a bunch of users, thousands of users spread over hundreds of projects. For example, here on our Joules cluster, Eureka system, and Joules booster system, which was the biggest system we had until last year, and it's still operating. So you don't need to read this all in detail, but it basically shows you that our users are spread over many different kind of research fields, and thus they have different kind of workloads and use cases stressing the system in different ways. So the compute, GPU, CPU, network storage, and so on. So we want to ensure that all of these use cases get the best performance in the end. So we need to look at different kind of metrics to make all our users happy. Then we do not have enough with the HPC systems, but we also have a bunch of different kind of quantum computers. One group is the analog quantum computers, and here we have the D-Wave quantum systems. Actually, the background should be blue, which is quantum annealer. That's written here in the white part. And we have a Pascal system that runs with neutral atoms. And we have even more quantum computers, universal quantum computers from different kind of companies, and different amount of qubits, and they are gate-based, they have trapped ion qubits or other kind of mechanism how they work. So this makes us also quite unique, not having only the biggest HPC systems, these variety of different kind of users, but also the quantum computers in different kind of configurations. So, and all of them are actively used, and they're not just standing there and burning energy, but we have users on them, software developers, the admins, and there are constant changes on these systems. So, and all of those might cause any regressions on those systems, or in the solution, in running the applications on them. And one way to keep track of them is to run periodic tests, or so-called continuous benchmarks. And this can be basically split into three different kind of parts. Running the tests, validating the results, and visualizing them in the end. So let's go through them one by one. So the easiest one is actually running them. So there are quite a few of solutions for this out there. We use and develop Jupe for this. This helps us to run this benchmark in a standardized, reproducible way. And we can collect the data in other repositories, databases, and so on. Then what's already a bit more difficult is the validation of them, because you need, a job can be successful, but it can produce garbage values, or you can get degradation over time, and that takes some effort to validate those results. And then the surprisingly hard part is to visualize them, because you need the historical trend of these data. Sometimes you need to compare with data from weeks or months ago. Or you need also the metadata, for example, if you want to look into what happened in this specific run, so the job ID, the software environment, and other kind of information, maybe the Git commit. And as this is so difficult, many people either don't do it, so performance drifts get unmonitored, or you do it manually, as I did a long time ago, or set up heavy database infrastructures to keep track of those. And what we would actually need is a dashboard that can turn these data that might be scattered over different sources, Git repos or databases, into an interactive dashboard. And ideally, you can do this without having to write any front-end code. So you just provide the data and the configuration, and the dashboard does the visualization for you. And the nice thing is, we have a software already that does something similar, but in a different kind of context, and that's called LLview. And the view that you're seeing here is a table and a list with jobs. So we collect data from Slurm, from the storage, from NVIDIA drivers, and many more sources, gather them together and create job reports or information that we provide to the users per job. And we can provide this in different kind of forms. Here we have the table view with some graphs at the bottom. And just to show that this is all configurable, and that's actually what we need, just not for monitoring the job itself, but keeping track of the results of our benchmarks. So how does this look in practice? Let's have a look at a simplified scheme. So we have our data sources that we have in LLview already, or that from which we get data into LLview. For example, from the Prometheus databases that our admins runs, from Slurm, from other daemons, and more. And then we have the LLview managed databases, and those ones are configured by just a few YAML files. So you write some YAML files, no SQL statements, anything, and with those you configure the databases, and they load the data from the monitoring infrastructure and does some analysis on them. And then the second part is another component of LLview, that is the web-based portal. And this portal creates views on the data. For example, the live view, where we can see actually what happens on each node of the system, or the job dashboard that we just saw on the slide before, the job reports that you see here on the right side, where we have it either in PDF or HTML format, or any other kind of representations. And those views are already generated with a role-based access in mind. So if you are an admin or a support staff, you can see different kind of metrics than maybe the user itself, or the project manager might see all the jobs from a project, while the individual user might just see its own jobs. And also our mentors of the projects might see different kind of views in the end. And what do we have to do to make this already existing structure work for the benchmarking? We just replaced our data sources. So we take the data from either databases or Git repositories where we store the results of our runs, and we need to change the YAML files a little bit. And the rest of the infrastructure remains the same. Then you might remember this from the slide before. We this time create different kind of views, maybe a view for the HPC systems, a view for our QPUs, the quantum systems, and maybe others, and generate similar views on them, again with a role-based access. So how does it look like in practice? How do we run our benchmarks on our systems? We have a GitLab repo, and in this we store all our benchmarks and have a CI pipeline running, which connects via Jacama CI to our systems. And then, as I said, our benchmarks are implemented in Joop. We let Joop run on the HPC systems, and as soon as the jobs are done, we push back the data into the repo, this time as CSV format, and there LLview comes into place and gets this kind of data that we just generated on the systems regularly, like every month, every hour, depending on how we configure the pipeline. Now I want to show you how easy it is to configure the client, LLview. So basically you need to only write a YAML file that describes where the data is and what to do with the data. So we define the link to the repo, give the credentials, the tokens, and also define which files from the repo we would like to analyze. Then, I don't go through this in the whole detail. Basically, we have a list of variables that we would like to use later for visualization. And we can get these variables from different kind of sources, let's say. So either from the file names that are stored in the repo. For example, we extract the system name from the file name in this example. Or we extract further values like the timestamps, or for this benchmark, it's the HPC benchmark. We define the grid sizes that we use for running, and we can extract them from the CSV file. So this is the content of the CSV file that we store. So, yeah, and this you need to do for all the variables that would like later have to visualize them. And then we are coming already to the visualization part. This is just a few more lines of YAML code. And we can define in the top part which parameters we want to, or which columns we want to see in the table. And LLview automatically generates for every combination a line in the table. Then there's this part that just defines the X and Y axis and the tabs at the very bottom for each benchmark. So this is the visualization. So here we access the parameters that we extracted on the slide before. And we can even do group the graphs in the individual plots by using the group by feature. Here we group by the MPI task and the threads per tasks. And we can even hover over this graph, so we want to have this interactive to see also the metadata, and this can be done by so-called annotations. Here we are seeing, for example, the job ID and the software stage in which the corresponding benchmark has been executed. And there's even much more that you can configure if you want to, the color of the lines and many more, and this is all documented on our web pages. Okay, let's have a look at a few examples. So first at the HPC side and later also on the quantum computing side. So here we group the benchmarks. Here we have our top view is benchmark view, and then for each benchmarks we let it run maybe on different systems and different combinations. And in this view we have the list of the benchmarks, and on the right side you see actually the status of the last 5 runs, whether it was successful or something happened there. So this is the high-level overview, and then we go into one benchmark. For example, this is the HPC benchmark. Here we see that there's only one line in the table, so we just let it run with one single combination. And yeah, you know the graphs. On the x-axis we have the time, so whenever we run we get a new, we extend the graph. On the y-axis the corresponding metrics. And in this case it's the gigaflops and the runtime. And again you see the annotations. In this example, you see in the table above, we have even more configurations from different systems. This is a stream benchmark, and on the y-axis, you see different metrics than before. And on the bottom, we have multiple tabs, so for showing different kind of sub-information per benchmark. And in the last view, I would like to show you that we can not only visualize timelines, but also scaling plots. So here, every graph is basically one timestamp, and we see how the application scaled for this time. And so we can keep track on how the scaling might have changed over time. And here it looks quite stable, say. Then, what I also mentioned is, it's nice to have these data, but we also want to detect regressions or any kind of changes in the data over time. And this is a pretty new feature. I think this hasn't been presented anywhere else before. So you're the first one seeing that. So we have some intrinsic functions that are provided already by LLview. And this is the threshold, the rage validator. You can see on the left plot, there is a dotted line at the bottom for the minimum value, and on the right side, the maximum value. Then if you would like to detect outliers, there's also another function that does this automatically and marks it in the plot. and also regressions are detected. And if these intrinsic functions are not enough, then we also have an API that the users can access to implement their own validation functionalities. And yeah, that's about the HPC part. Now having a look in more details at the quantum computing side. So here we do not sort them by benchmark, but we have on the top view per system. So it's all configurable. And here we see, for example, our different systems that are currently tested, and on the right side, or again, the status of the last 5 runs. Then you might remember this view. There are 2 specialties here. The first one is that we have here some tabs on top of the table. So we have, this view is per system. So we might have run several benchmarks per system. And these tabs show the different benchmarks. So you can click through them. And this is also available for the HPC part. It's the top part here, and there you can give some additional information about the benchmark. So if we open this portal to users, for example, or to the colleague, and you add a benchmark, you want to also have a description, so what this benchmark is supposed to do to be able to interpret the results that you can see here at the bottom. Now, for the quantum computing part, I would like to discuss 2 specific benchmarks in a little bit more detail. So what did we detect with the tool, with LLview in that kind of context? And I'm not a quantum computing expert at all, but I need to thank my colleagues Ashwin and Carlos for explaining this all to me, and I hope I will be able to make this as easy as possible, because this annotation I also saw last week for the first time. So what this benchmark does is a very simple one. You have 2 qubits, and the first qubit you bring in a superposition between the value 0 and 1, so somewhere in between on the sphere. And the second qubit is entangled with the first one. So what this says is that if we measure it, if we measure the first one, then this defines also the value of the second one. And in such a way that if we measure the first one and the first one has the value 0, then the second one will also be the level 0. So we have the state 0, 0. Or if the first one is measured as value 1, then the second one will also be value 1. So we expect in 50% of the time a state of 0, 0 or a state of 1, 1. But what we do not expect to see is states that is either 0, 1 or 1, 0. And this is the benchmark. So this is a very, very basic entanglement benchmark. And what we see here is on the x-axis again the time that we executed the benchmark. This is already running for more than a year. And on the y-axis the probability in which the different states was measured. The blue and the red one here in the middle are the states 0, 0 and 0, 1 with about 50%. And at the bottom we see the other 2, which are 0, 1 and 1, 0. And you see there's a lot of noise in there. Doesn't look like it's perfect. So why? So what do we see here? This is the most obvious one. The system was not available, either the QPU itself or the system that we use to connect to the QPU, which is called Captiva, that we also use to connect to our supercomputers. Then these ones. Here we see slight ramps up, and these are uncontrolled temperature raises. So the system wasn't in a good state. So if a user, for example, has run its job in this period of time and can have access to these data, they know the problem is very likely not their problem, but the problem of the system, because the system wasn't in a healthy state. The next example is this one. So experts might see here that the single qubit is a little bit miscalibrated. And this part is also very interesting because there the default transpilation changed. So you can imagine this as a change from compiling with 03 versus 00. So before we compiled with 03, so the highest compilation level. And this you would want to do when you don't care how the solution was achieved, but just you want to get the solution with the highest performance. And you use the O0 when you really care on how you achieve the solution. And here the change to O0 happened, and this causes this noise that we see here. Then I have a second example here. This is also, I also try to explain this in a very easy way. So this is the identity. So we initialize all our qubits with the value 1. And then we apply 2 rotations on them so that it gets back to the state 1. And then we measure again. So in the ideal case, we would expect that independent on how many rotations we do, it always ends up when we measure at the state 1. But what do we see here? It's not that everything will be in the state 1. On the x-axis again, we have the time, and on the y-axis the probability in which the values are all measured as 1. And you see here, it never reaches the value 1. And these individual lines that you see here, these are the rotations, so 0, 10, 20, 30, and so on rotations that we did. And I will explain a little bit more in detail what we see actually in these graphs. So this is just to set the environment. The first one, this is the first part where we started with it. We had the highest transpilation level activated, and this actually recognizes that there's a 0 operation. So if you want to be in state 1 and then you want to be in state 1 again after an undefined amount of rotations, then this compiler recognizes, or transpiler recognizes that you don't have to do anything. So there's actually no operation applied to the qubit, and even in this state you see it doesn't reach the 1 line here at the top. So this is what we see here. So the compiler actually is smart enough to detect that it doesn't have to do anything. Then the second block looks already a bit different. Here the transpilation level has changed. So we see already more variation as we have seen before. And to compare this to the next part that I'm going to talk about is that here we have applied this operation only to 2 qubits out of the 5 qubits in the system. And this, you can see, compare it to the later ones, has less errors. And this is because the errors are proportional to the amount of qubits that are used. And that's what we see actually here. So if we use 5 qubits, we get much, much more variations and even worse results. What else do we see? So this blue line here at the top is actually where we apply 0 rotations. So we initialize and we measure. And even when we do that, we see that there is an error of about almost 20%. And this is called the state preparation error. That's what we also see here in these kind of plots. And then in general, one can say that the gate error, so these rotations are gates that you apply, accumulate with the increased depths, and depth is the amount of rotations that we do here. So it goes quite low here, the more rotations you do. So the systems are not as super stable and evolved yet as HPC systems. And yeah, these were the discussion of the examples. Now let's have a quick look on a few things that we are still working on or would like to work on in the future. I've already showed the validation feature. It's not yet released, but it's going to be released soon. We would like to add more benchmarks on the HPC side and the quantum computing side to keep track of the different kind of use cases that we and our users have. And we would also like to make this available for users and projects so that they can bring in their own applications and that they only see also their own applications and not all our other users see them. This is also actively being worked on at the moment. Then I'm already coming to my conclusions. So I've showed you that we have created a flexible framework that lowers the barrier for such kind of analysis. We decoupled the execution from the visualization, so you can execute your benchmarks however you like, just need to provide the data in the end, and LLview takes care of the visualization. Then we have implemented this automatic validation. We give historic context with the metadata, and and thus we are empowering the hosting entities and also the users to catch these performance changes. And everything is open source, it's documented, and with that, I would like to especially thank my colleagues Felipe and Wolfgang, who are developing LLview, and Ashwin and Carlos, who helped me to look a little bit like a quantum expert, which I'm not at all. And they are running the quantum computing benchmarks. And and if you're at the ISC next week, we have 2 posters, a talk in the Moda workshop, and actually 2 booths where we show LLview, and also our quantum computing experts will be available. Thank you.
Do you want to go ahead with
okay. You made it look almost too good to be true in ways of configuring it. So let's say I have some spare space in my living room and I want to put a quantum computer. How really easy it is to configure this for this kind of machines? It's just a YAML.
This is independent of supercomputers and independent of quantum computers. You just need a server to run LLview on. Does this?
But I mean the learning curve of configuring LLview.
There are examples, we provide basic examples, and there's a bunch of YAML scripts. I've never configured LLview myself, as I'm a user of this infrastructure, but my colleagues will help you if this is an issue, but there's also examples available for that, and we have all been working with other centers, and this seemed to have worked out for them. So unfortunately, I don't know the exact details on how to configure it, but it's supposed to be just YAML files, and you don't have to write any SQL statements and so on.
Okay, but do you need to be a hardware expert? Do you know that? To configure
Hardware
it?
expert? No, I think this is independent of the hardware. This is just the software that you need to install on the hardware.
Okay, thank you.
Thank you, Thomas. So I have a question, and it's slightly related, but regarding how you run the benchmark, right? You mentioned you only have to provide the data, right? But what are you using actually on your side to run the benchmarks? Are you using any specific benchmark framework like Reframe, or you have your own internally?
I'm coming there soon. This is actually our environment. So we have a GitLab server, and there you can run CI pipelines, and this authenticates to the supercomputers via Jacama. And we don't use Reframe, we use Jupe, because we developed Jupe. And we have implemented all benchmarks in Jupe. And this is also what we did for the procurement for our exascale systems. So usually when we procure systems, we need to provide also benchmarks for the vendors to validate against, and we provided them in the Jupe description formats. And all the benchmarks that we run, they are implemented in Jupe, and then Jupe's getting executed on the login node of the HPC system. That's the HPC system part, and they execute it via Slurm on the cluster part, and then the values gets back, and we push them back to the repository via the CI.
And Job already generates this CSV file ready for
exactly. So you can tell Joop how to run, how to compile, or you use, for example, Easy or EasyBuild as an infrastructure to have the software compiled, and Joop, you tell Joop basically how to run it then and how to extract the result data that you would like to see. And this time it's in a CSV form, but you can also have plain text or databases. And then we decided here to do it in the easy first approach with CSV files. We push it back to the repository, and this is where LLview then can hook in. And so LLview is completely independent of these kind of infrastructure. So if you have Reframe or something else, or just data sitting somewhere, you just need to give LLview kind of access to it, and it can work independently of this infrastructure.
And just a follow-up question, are all your job benchmarks available online?
Yes, I'm not sure if all, but at least the ones that we have used for the procurement of the exascale system. We call it ubench. This is on GitHub. All these recipes are on GitHub. Yes, there are also other sites publishing Jup files, but this is how we started, and we would like also continue this way. So this is a good starting point to actually get started with Jup. Yes.
Thank you.
Thank you.
Thank you so much.
Yeah, here.
Okay.
Hi, Thomas. First of all, congratulations for the presentation, okay? I was wondering, maybe this is more like an implementation question, because imagine I want to submit some jobs that I have performed for quantum machine learning, let's say, and this will have different architectures, okay, for the circuit. I was wondering, how do you pass from my results, which are going to be a little bit structured, but will have different features, characteristics, results, metrics, whatever, to your own visuals? Like, how do you pass from my unstructured data that you don't know to having something structured so you can visualize it, you can have this benchmark?
You are basically asking about, I mean, all our benchmarks have different kind of metrics.
Okay.
They show the runtime, the gigaflops, and the quantum benchmarks even have completely different kind of metrics. And LLview is independent of these metrics.
Okay.
You just need to provide the data itself, and you need to have some kind of ordering in there. Because you want to sort them in a specific kind of way. And by providing these kind of YAML files, I think this is automatically done. So for example, if you have your data in CSV files and in table format, then you describe how to extract this from the file by just adding the column names, for example, or using regular expressions to extract the data or other kind of expressions, and then LLview can visualize them for you. But I'm not 100% sure whether I really got your question the right way.
That was
Okay, thank you.
Thank you.
So thank you so much. Let's leave the questions for the coffee break, because we are a bit tight on the time.
Yeah.
Thank you so much.
Thank you.